Experiment number 33. Comparison of electromotive forces of two cells using the potentiometer. Experiment number 34 is also a potentiometer experiment. It's the determination of the internal resistance of a cell using the potentiometer. So before doing these two practicals, we need to understand what a potentiometer and how it works. So potentiometer has a main circuit. As you can see here, we call this the main circuit. So in this main circuit, you have a cell. You call this cell the driving cell of the potentiometer. A switch, it has to be a plug switch, and a resistor. So in this main circuit, the other main part that you have is the potentiometer wire. Potentiometer wire is a uniform wire. A uniform wire in the sense it has a uniform cross-section area, as well as this potentiometer wire's material is usually manganese or constantan. So this wire has a property of low temperature coefficient of resistance. So with the temperature, its resistance only changes slightly, not much. So we'll first take a look at this main circuit and we'll see how the main circuit works. So you can see it's a single loop circuit. So once you switch it on, there will be a current flowing through this wire. So in this wire, each length, let's say each centimeter, has a constant resistance. So I'm going to show that to you using this equation. R equals rho L over A. Rho is a constant value for this, and the area of cross section is also constant. So the resistance of this wire is directly proportional to its length. So each centimeter has a constant resistance value. So the potential drop per unit length in this wire is constant, right? So we can say potential drop of this wire is proportional to the resistance. Also you can say it's proportional to the length. So if you take 1 centimeter of length in this wire, if it has a potential drop of V, if you take 2 centimeters, that's 2V. If you take 3 centimeters, that's 3V. So the potential drop in the wire is proportional to the length that we consider in that wire. So in order to explain it further, I'm going to mark a few dummy potential values here. So I'm going to mark the potential at this point as V, and I'm going to mark the potential at this end as V minus 6. So here my assumption is that the potentiometer wire has a potential difference of 6 volts. So it's an assumption. It's an assumption. So I'm assuming the potentiometer wire to have a potential difference of 6 volts. So if you divide the wire into 6 equal sections, each and every one of these sections will have a potential drop of 1 volt, because we understood that the potential difference in the wire is directly proportional to its length. So here we can mark it's V minus 1, V minus 2, V minus 3, V minus 4, V minus 5, V minus 6 likewise. So the potential drop here is directly proportional to the length. So now we are going to talk about this secondary circuit that we have in this, where we have the cell that we want to measure. This is that cell. I have taken a dummy value for that also as 3 volts, a Zenta0 galvanometer, and a contact key. So now the contact key, as you can see, is not connected to anywhere. Now this contact key's purpose is to keep it on the wire from point to point. You can keep it on the wire. Here the potential at this point we took as V, and the EMF of this cell is 3 volts. So the potential at this point is going to be V minus 3. Since there's no current, there's no potential difference of the galvanometer. So here, anywhere in this wire, it's V minus 3. So on the contact key also you have a potential of V minus 3. Now along the wire you have potentials which reduce with the length, V minus 1, V minus 2, likewise I have marked the points. And there is a point on the wire also which is equal to V minus 3. And the potential on the contact key right now is also equal to V minus 3. So if you contact this point, if you bring the contact key and connect it to this point, there will be no current in the galvanometer because there's no potential difference. You are going to connect V minus 3 potential to again V minus 3 potential. So we are going to connect two points which have the same potential, so there will be no current passing through the galvanometer. So this point has a certain name. We call this the balance point, right? The point at which where the galvanometer gives a zero deflection, we call that point the balance point. So when you keep it at the balance point, at that instance, the EMF value that you are going to measure is equal to the potential difference of the wire in this part. The EMF of the cell that you have here is equal to the potential difference of the wire of this part that you can see. So if you keep the contact key at this point where it's V minus 2, V minus 2 has a higher value than V minus 3. So if you keep that, if you keep the contact key at that point, there will be a current flowing towards this direction through the galvanometer. If you keep it at V minus 1, the potential difference will be 2 volts. Again, it will move to the same direction. So if you keep the contact key to the left hand side of the balance point, you will be getting the current flowing towards this side. If you keep the contact key at V minus 4, V minus 4 is a lesser value than V minus 3. So there will be a current flowing towards this direction. So through the galvanometer we have a current flowing towards this direction. Also if you keep that as V minus 5, then again the current will flow towards the same direction. So you can see that since this is a center zero galvanometer, if you are going to keep the contact key either to left hand side or either to the right hand side of the balance point, there will be deflections towards two different directions. There are two directions in the center zero galvanometer, so it will go towards both directions. So here we do an important check before getting a measurement in this device, is that we are going to keep it at this very end as well as this very end at the beginning of the experiment. So when you keep it at those two ends, if you can get deflections towards both directions in the galvanometer, then we can say that there must be a balance point somewhere in the wire. If you do not get deflection going towards both directions when you keep it at the two ends, this very end and this very end of the potentiometer wire, then we have to think that there is something wrong with the device, so we don't get a balance point. So this is the basic principle of this potentiometer and how it works. So I think you got a good understanding of how it works. So at the balance point, you can see that there is no current passing through the galvanometer. That is why we call that the balance point. There's no current passing through the galvanometer, or no current passing through the cell. So therefore, whatever the internal resistance of the cell, it does not get involved in the potential difference. It is just reading the EMF of the battery. So the potential difference of the potentiometer wire up to the balance point is equal to the EMF of the battery at the balance point. So therefore, this device can work as an ideal voltmeter. This device works as an ideal voltmeter. Right. So now here what we have is the potential gradient. So we are going to learn about the potential gradient, or K of a potentiometer. So K is defined as, or the potential gradient is defined as, the potential difference per unit length of the wire. Potential difference per unit length of the wire. So how do you explain it? So if the potential difference of the wire is V, and if the length of the wire is L, K is equal to V over L. So the unit of that potential gradient is volts per centimeter, or you can also say volts per meter, but usually we use volts per centimeter unit. Right. So how do we find the potential gradient? How do we find the potential difference of the wire and divide by its length? So we know the length, but it's very difficult to find the potential difference of the potentiometer wire. So therefore, what we do is that we are going to balance this potentiometer with a standard cell. So we use a standard cell in order to balance this potential, in order to get the balance point of this potentiometer, and with that we are going to find the value for potential gradient, or K. So finding K is known as calibrating a potentiometer. This process is known as calibrating a potentiometer. So let's take a look at what a standard cell is. In the laboratory you have standard cells. A standard cell is an accumulator. An accumulator is a battery which has a constant potential difference throughout the time, even though it is depleting its potential difference, or the EMF is not changing. So that is why we call it an accumulator. So a standard cell is also an accumulator with a precise EMF stated on it. So usually in our laboratory what we have is a standard cell of EMF 1.0183 at 25 degrees Celsius. So on itself it's being stated that it gives an EMF of 1.0183 at 25 degrees Celsius. You don't need to memorize these values. You don't have to memorize these values. So all you need to know is a standard cell is a battery which gives the precise EMF at a certain temperature. So what we do is we find the balance point using this standard cell. So at the balance point we can say the potential difference of the wire is equal to the standard cell's EMF. So we can say ES is equal to KL naught. K is the potential gradient, that is the potential drop per unit length. So when you multiply that by the balance length, the length from here to here, we call it the balance length. So when you multiply K by the balance length, you get ES. So you can subtract K here, that is ES over L naught. We know the ES value, we can measure L naught value using a meter ruler, so we can find K. So finding K of a potentiometer is known as calibrating a potentiometer. So let's see, how do we find an unknown EMF using the potentiometer? So you know that now we have found K value, and if you use an unknown cell and if you balance it with the potentiometer, if you find the balance point for that EMF source or the battery in that potentiometer, and if you get the balance length as L, you need to multiply L by K, the potential gradient, in order to find out this E, because we know at the balance point this EMF is equal to the potential drop in the balance length. So it's KL is equal to E. So this is the main equation that we use in potentiometers. The main equation that we use in potentiometers, E equals to KL. So when you can measure L, if you know K, then you can find any unknown EMF using the potentiometer. Right. So let's see what are the reasons for not being able to get a balance point. There are a few reasons that we cannot get a balance point. So one reason is that the EMF that you are going to measure is being greater than the potential difference of the potentiometer wire. So if you are going to measure an EMF which is greater than the potential difference of the whole potentiometer wire, you can't measure it. You can't get a balance point. It is not getting balanced. Right? So the potentiometer wire should have a potential difference which is greater than the EMF or the potential difference that we are supposed to measure. So if the potentiometer wire's potential difference is not sufficient or not enough or is less than the EMF that we want to measure, then you don't get a balance point. The deflection will be always towards one direction, not to both directions. Right. The second reason is that the terminals of this cell are being interchanged. So I will go to the previous example. If the terminals here are being interchanged, now I'm going to change the terminals here. So if the terminals directions are now interchanged, then the potential here is V. So the potential here won't be V plus 3, instead that will be, or won't be V minus 3, instead that will be now V plus 3. So on the contact key we have a potential of V plus 3 now, but on the wire anywhere we cannot find V plus potentials. On the wire we have all V minus potentials, but on the contact key we have a V plus potential. It's more than V, and on the wire it's less than V. So when you keep it at any point on the wire, if you keep the contact key at any point on the wire, still you can't find a balance point. Always currents will be going towards this side of the galvanometer, because here the potential is greater than the potential of the potentiometer wire. So this is one of the reasons that why you cannot get a balance point. So you have to connect both of these cells towards one direction. Now this cell is towards this direction, this cell is towards this direction. So if you are interchanging the terminals of this, then you also will have to interchange the terminals of this in order to get a balance length. Otherwise you don't get a balance length. So there are two reasons we discussed right now why we don't get a balance point. Third one might be disconnections in the circuit. So if the wire has been disconnected from here, there will be always current flowing towards this direction, so there's no balance point. Depletion of the driving cell. If the driving cell is fully depleted, then also the potential difference here will be less, so there will be a current flowing towards this direction. So these are the reasons why we don't get a balance length using a potentiometer. Right. So now we are going to discuss another critical point in the potentiometer, which is comparing two EMF using the potentiometer. Now we are going to that experiment, the first experiment that we were talking about, right? So here you can use two EMF sources that you want to measure. You can see there are two EMF sources, two batteries connected to the potentiometer, E1 and E2. So what you can do is you can put this switch to E1 side and you can get a balance length. Let's call it L1. So you can say E1 is equal to KL1. That's our first equation. Then you can switch it here and then you can find the balance length for that. Let's take that balance length as L2. So you can say E2 is equal to KL2. That's our second equation. So we are going to divide the two equations. E1 over E2, K gets cancelled, is equal to L1 over L2. So you can say L1 is equal to E1 over E2 into L2. So this makes a perfect graph equation y equals mx. Gradient of the graph is going to be E1 over E2. But we have a problem here. The problem is, how are we supposed to get different L2s and different L1s? Because for E1 you get a certain L1, for E2 you get a certain L2, and L1 will not change with E1 unless you change the battery, but we can't change the battery as well. So we find it difficult to get variable lengths in this experiment. So we use a small trick here. The trick is we use a variable resistor, a rheostat here. So when you use a rheostat, and if you change the resistance of the rheostat, the K value will change. The K value here will change. So what you do is that you keep this at 1 resistance, and then you get 2 balance lengths for L1 and L2. And then you change it a slight bit. So now it's a different K, so it's a different L. So you get another pair of L1 and L2. Then you change it once again, you get another pair of L1 and L2. Likewise, you are going to change the value of this. You don't have to know the value. You don't need to know the value, you just have to change it. So you get a different L1 and L2 values. So once you change it once, you have to get 2 readings before changing it again. You have to get both readings at once before changing the value again. So for every K value, you should have a pair of L1 and L2 values. So once you get sufficient number of L1 L2 pairs, at least 6, then you can start drawing the graph. So when you draw the graph, you'll be getting a y equals mx type of a graph, and from the gradient of the graph you can obtain the ratio of E1 over E2 value. So the potentiometer does not need to be calibrated in order to do this question, because you don't need K, as K is getting cancelled, and K also changes time to time. So K is not necessary to be found in this experiment. The second experiment that we are going to do using this device is finding internal resistance of a cell. So now it becomes a little bit complexer than we discussed before, since we are going to attach another circuit into this potentiometer. So let me explain to you what we do here. First of all, we are going to balance the battery that we have without this secondary circuit. We're just going to balance it without this secondary circuit. So if you get a balance length L0, then you can write down an equation. E is equal to KL0. E is equal to KL0. Then what you do is, then you are going to make this circuit using a resistance box here. This is a resistance box, right? So when you make this circuit, you know this circuit is a closed loop. So if you have a closed loop with an EMF source, there should be a current. So there will be a current flowing this way. And we are only talking about the balance point. Since we are only talking about the balance point, at the balance point, we only have 2 currents in this circuit. One current is in the main circuit, and this other current is in this circuit. There is no current through this path, there is no current through this path. There are only 2 currents, right? So since we have that idea with us now, let's see what is the potential difference that we are going to measure. What is KL? Now you balance this device again, so you get the balance length as L. So this KL is the potential difference here, this potential difference KL. You know that potential difference must be equal to this potential difference. Also, you know that potential difference is equal to this potential difference. So we have three potential differences which are equal to each other. So we can first say this potential difference, that is I into R, is equal to KL. So we write an equation IR is equal to KL. So I, we can say, is equal to KL by R. Then we can equate this potential difference to this potential difference. So what is the potential difference of a cell when there is a current flowing through that cell outwards? V equals E minus IR. So we can say E minus IR is equal to KL. So we have our second equation as well. So now we have three equations, 1, 2 and 3. So we are going to combine these three equations. So for E, we are going to substitute KL naught here. For I, we are going to substitute KL over R. So once you substitute, what you get is KL naught equals KLR over R. KL naught minus KLR over R is equal to KL. So these K's get cancelled. K gets cancelled. So you get an equation L naught minus L simple R over capital R is equal to simple L. So here we need to draw a graph in order to find out the internal resistance. We can also find out the internal resistance just using this equation, but we are not doing that. We are drawing a graph to get more precise or to get more accurate results. But when we are doing questions, all we do is that we get these three equations and we just simultaneously solve these equations to find out the internal resistance. That is how we do the questions when in MCQs and all. That is how we need to do. But in this one, what we do is that we rearrange the equation in a way that we draw a graph. But you can see when you look at this, the variables that we have are the R, and according to the variation of R, L will change. So you can change R. So with R, L will change, because when you change R, the current of the circuit will change, so the potential difference here will change, so the balance length will change. So your independent variable in your x-axis, you should have R, or the resistance box is valid. In your dependent variable or in y-axis, you should have L. So there is a problem in this equation. In this equation, there are two L's here, and in one term you have R as well. So you can't get directly R for x-axis and directly Y for L for y-axis in this. So we have to rearrange the equation in a way that 1 over R becomes the x-axis and 1 over L becomes the y-axis. So this is a skill that you have to practice if you are writing the structured essay questions, because they will be giving you variables and an equation, so you have to rearrange the equation in a way that you get a graph equation. So I am going to rearrange this equation so that I get a graph equation. You can see that. So first of all, I divided both sides by L naught. So when I divide it by L naught, these L naughts get cancelled, these L's get cancelled. So now what I get is 1 over L is equal to simple R over L naught into 1 over capital R plus 1 over L naught. This will give me a graph equation just like y equals mx plus c. So all we have to do is we have to draw the graph between 1 over R and L. So from the gradient of the graph you get simple R over L naught, and since we know L naught, what we can do is that we can just divide, or just we can multiply the gradient by L naught and we can get R value. But we can do the practical without getting the L naught value as well. We can determine the internal resistance without finding the L naught value as well. How is that? Is that you divide the gradient by the intercept, because in the intercept you have 1 over L naught, so it gets cancelled. So when you divide the gradient by intercept, this is what you get, it's equal to R. So this is how you find the internal resistance of a cell using the potentiometer. So the key point here is that we have 3 potential differences which are equal. So why do I say that these 3 potential differences are equal? Once again, I'm going to explain. Because this point and this point, they are connected with resistanceless wires. So all these 3 blue color points have the same potentials. And here, this point's potential is equal to this point's potential is because at the balance point there is no current flowing through the galvanometer, so there is no potential drop when you go along this path, and that potential is also equal to this potential, so that you can say this potential difference is equal to this potential difference is also equal to this potential difference. And this is the key concept of doing the questions in the potentiometer, finding internal resistance of cells. Right, now you know how to find the internal resistance of a cell using the potentiometer. And now we take a look at the key points in a potentiometer. So one of the key points is that the contact key must not be slided or hardly pressed against the potentiometer wire. If you do so, that might damage the cross section of the potentiometer wire, so that its length will not be proportional to the resistance, so that it will not have a constant potential gradient. So if you don't have a constant potential gradient, your values will not be accurate. So we are not going to slide the contact key on the wire, neither we are going to press it hard on the potentiometer wire, and if you do so, you do not get correct values. Fine. And the next point is that the wire is made of constantan or manganese, so it has a very low temperature coefficient of resistance. There's a very low temperature coefficient of resistance. So even though when we do the practical, you know, when the current passes through the potentiometer wire can get hot, so its temperature might increase. So you know, when the temperature increases, the resistance will also increase, but it doesn't happen here, as the temperature coefficient of resistance is very low in this particular material. The next point is that another one that we have already discussed, that before getting the measurements, before finding the balance length, we are going to keep the contact key at the 2 ends of the potentiometer wire. So when you keep the 2 ends, when you keep the contact key at the 2 ends of the potentiometer wire, you should be able to see that the deflection of the galvanometer is going to go towards both directions. And if not, something is wrong. And if yes, then we can get a balance point. So when you do that, we find when you do that, there is a problem that we are going to face. So let's see what that problem is that we are going to face. So I'm going to take you back to the previous slide. So here, when you keep it here at this very end, the potential difference will be V and V minus 3. Those are the potentials. So the potential difference is going to be 3 volts. And when you keep it at this very end, here also it's V minus 3 and V minus 6. So the potential difference is going to be 3 volts. So you know, when you go away from the balance point, the potential difference increases, and when you keep the contact key at the very ends, that will be the highest potential difference that you will be getting in between the terminals of the galvanometer. So if you are going to do this, then there must be a safety procedure that we are going to follow. Why? Because we are going to keep the contact key at the highest potentials. So there will be the highest current passing through the galvanometer. So unfortunately, if it cannot bear that, the galvanometer's coil will burn. So we will have to replace the galvanometer. So we have to make sure the galvanometer is safe. Right? So why do we need to do this? Because we are going to keep the contact key at this very end and this very end at the beginning of the practical. So it's like we are risking the galvanometer at the very beginning of the practical. So in order to prevent the galvanometer from getting damaged in this particular exercise, we are using this setup as a protection device. We are using this setup as a protection device. So we have a switch here and we have a resistance. So what will happen is that when you keep the contact key at the very ends, the potential difference is high, so the current will also be high, so the galvanometer might get damaged. But now current is not going to be high because the current needs to go through this resistance. When the switch is off, current needs to go through this resistance. So the resistance is high, so the current is now at an average value. So it's not as higher as we think it is. So this is a safety device. So you might think, why do we need to use a switch? We can keep the resistance alone. But the problem arises when you come close to the balance point. When you try to find the balance point, there's going to be a problem. Because when you come close to the balance point, you know the potential is reducing. Potential difference is reducing. And when you have a higher resistance at that time, as a result, the I value is going to be very low. Since the potential is low, the I will be low. Since the resistance is high, then also I will be low. So therefore, you'll be getting a very low current close to the balance point. So this makes it difficult to find the balance point. This makes it very difficult to find the balance point. So what you might find is not just one balance point, but a range, a balancing range. So on the wire there will be a range of length in which everywhere you get zero deflection. Why? Because you get a very small current that you don't see that current in the galvanometer. So what you do is that when you find the balance point closely, then you are going to switch this on. You are going to switch on. So when you switch on, the resistance is now neglected. The current does not pass through the resistance, instead it will go through the switch itself. So we are again dropping the resistance by switching this switch on. So when do we switch it on? Only when you find the balance point slightly, or when you come closer to the balance point. So when you keep it at the very ends, you are going to switch it off. Right. So let's check what are the advantages and disadvantages of this device. The advantages of this device is that it works as an ideal voltmeter. It's an ideal voltmeter. So it does not absorb a current, because we are getting measurements at the balance point. There's no current flowing through the cell that we are going to measure at the balance point. So it works as an ideal voltmeter. It has a higher sensitivity. We can increase the sensitivity as well. It has a higher sensitivity because you can change the length of the wire. It doesn't have to be 1 meter exactly, just like in the meter bridge. You can have 2 meters, 3 meters. So you might wonder, how do you get 2 meters and how do you practically maneuver it? So when you have 2 meters of length, what you do is you connect 1 meter of the wire like this and the other 1 meter of the wire like this. So you can just increase the length of the wire just by connecting it like this. So you can increase the length of the wire by connecting it like this. So you don't have to have this 1 meter here, you can have higher lengths than that. So it has a higher sensitivity. Also, we can use it to compare EMF sources. The disadvantages: it's a large apparatus to use and it's very complex, right? It's not just a plug and play device. If you take a voltmeter is a plug and play device. So we are comparing the advantages and disadvantages with a voltmeter, you must remember. And the second one is that it's time consuming. If you have a voltmeter, it will give instantly what the value is, but this we'll have to balance first, then we'll have to do a small calculation to find it out. So this is not a very good device to find quickly changing voltage values. You can't use this device to find quickly changing voltage values. And also, the range is limited. You can't find very high potential differences or EMFs, because in order to do that, we'll have to have a driving cell of bigger EMF as well. So the range is limited. And also there is another advantage that we did not discuss. You can use this to find out the internal resistance of a battery. So this is another advantage that we have in this device. So I think you got an idea about the potentiometer and its uses and the two practicals we have.